x to the fourth, we already use this method. X to the fourth, we use two multiplications. Remember, the first multiplication, x times x. Second, x squared times x squared. We already used this method. So, but at that time, I didn't give you the name of this method. Here, that's the repeated squaring technique. Yeah. Because we can do this way repeatedly, and we can calculate any power of x number quickly. Yeah. All right. So here, let me run the whole method. How to evaluate the monomials efficiently. Yeah. Here we only look at the monomial evaluation. Yeah. Given a monomial x to the n. Yeah. How to find an efficient way to calculate its value. Yeah. Here we use that repeated squaring technique. We try to do square operations repeatedly. Okay? Yeah. So that's the basic idea. Yeah. So here I also give you the reference in our textbook, section 6.5. Yeah. All right. Analysis. Yeah. What do we have so far? Yeah. Let's see. We apply Horner's rule to evaluate a polynomial. Yeah. So, but the Horner's rule, if you look at the details, that's the general way for a given polynomial, not a special way. Yeah. For any given polynomial, we can apply the Horner's rule. Yeah. It's a general method. All right. But it does not mean for a special polynomial, Horner's rule is the fastest. It does not mean that, right? Yeah. It means, so if you have a very general formula, then the Horner's rule gives you a very efficient way. But it does not mean when you have a very special polynomial, Horner's rule is the fastest. No, it's not that. Horner's rule may not be the fastest. For a special polynomial, we may have other faster way than the Horner's rule. Yeah, so that's the main point here. All right, yeah. For this general rule, a general polynomial, yeah, so we are satisfied with efficiency of this algorithm in general, Horner's rule. Yeah. All right. How about the special cases? Some cases are very special. Yeah. If you still apply the Horner's rule, then not the fastest. Yeah. Can we do better in certain special cases? Yeah. Yeah. Here, the monomial is a special case. Monomial. Yeah. If you still apply Horner's rule on monomial, then very slow. Okay? Very slow. Not good. Yeah. All right. Now we consider special cases. Yeah. Yeah. We saw this example. Yeah. Here, our old example, x to the fourth, we use two multiplications. Yeah. So you know how to do it. Yeah. Repeat it, squaring. Yeah. First one, x times x, the first multiplication. Second one, x squared times x squared. So we skip x cubed. We do not need to find x cubed. Why you need x cubed? Right? So we skip that step, that multiplication. Yeah. If you want to take x squared times x for x cubed, not needed. So we save that multiplication. So we can do a little better for this x to the fourth. Yeah. All right. Yeah. So here, the reason we can do better, we apply this repeated squaring technique. Okay? Yeah. Now we want to extend this technique to cover more power of x. Yeah, we can calculate. Yeah. Let's first consider x to the nth with n is a power of 2 number, special. N is a power of 2 number. So how well we can do? Yeah. Let's try. Let's do experiments. Yeah. Yeah. When k, yeah, so here, yeah, let's do the chart. Yeah. First column k, second column x to the nth. Yeah. All right. Then we count the number of multiplications, third column. Okay? Yeah. When k equals 1, x to the 2 to the first, right? Yeah, because, you know, k equals 1, n equals 2. 2 to the first. 1 multiplication. Yeah. Simple. When k equals 2, we just did it. X to the fourth, 2 squared, right? So the number of multiplications we need 2. Yeah, also 2. Okay, all right. Let's do another one. K equals 3, x to the eighth, 2 to the third, eighth. We just do another multiplication, x to the fourth minus the x to the fourth to get x to the eighth, right? We add 1 more. Because after we get x to the fourth, how about we use x to the fourth minus it, multiply itself. 1 more multiplication, we get x to the eighth. Yeah, 1 more, so 3, and so on. Okay? Now you can answer the general case, right? Yeah. After these 3 simple experiments, now, So we do not need to do more, right? It's enough. Okay? We find the rule. We can observe the rule clearly. Yeah. When k equals general number k and x to the 2 to the kth, yeah, power of 2. Yeah. Now you tell me how many multiplications based on the rule you observed. Yeah, based on the first 3 experiments. Can you tell me multiplications? Use induction? Induction? Yeah? Okay, yeah. Same number. Same number. Yeah. Yeah. Induction. Okay? Yeah. All right. It's correct. Yeah. Because it's so simple. So we do not need to prove mathematically. Yeah. So we can do it easily. Yeah. Yeah. So it's enough. Yeah. All right. Okay. All right. Now you can see here I want to show you how much improvement if we do in this way. Yeah. Let me use the example when k equals 10. When k equals 10, 2 to the k equals x to the 1024th. That 1,000, more than 1,000. Okay? Yeah. Think about if you use ordinary way, if you do not use this special way, use our old way, how many multiplications you need? If we just use our old way, multiplication, every time multiply 1x, how many multiplications? Good, perfect. 23, not 24, okay? 1023, because the leading coefficient is 1. 24, if you want to say 1024, that's the case if the leading coefficient is not 1. Suppose you have some coefficient, extra coefficient, ak, then you should add 1 more. If the leading coefficient is 1, reduce by 1, because you don't need to multiply any coefficient. Okay? All right. Yeah. So here, the answer is 1023. Yeah. Then, using our new method, repeated squaring, number of multiplication is 10. How big difference between these two numbers? 1,000 something versus 10. How big is the difference?
1013.
Yes, that's difference. You can see, if we take away 1,000, if we just use 23 to compare 10, already much bigger, right? Yeah. Even we don't look at 1,000, 23 already much bigger than that 10. So you can see how much you can save. All right? You can see this repeated squaring. So good. So good. Okay? All right. Yeah. But the thing is, that's for n is a power of 2. If n is not power 2, can we still use this repeated squaring technique? Yeah. Because if this method can only be applied to power of 2, still too limited. Because most of the time n is not power of 2. So we want to extend it to any n. Yeah. So our next step. Yeah. All right, before we go to the extension to cover all positive integer n, let's look at the essence of this method. Why we have this big improvement. The essence of this method. Yeah. Reuse the resource as much as we can to save operations. Reuse the resource. Yeah. Here, I want to, give you this idea. Yeah. Yeah. Because many times you already have a lot of resource. Yeah. When you build up, yeah. Yeah. Because when you do investment, you pay, you already pay to, you buy a lot of things. Try to reuse your resource. Do not waste. Do not buy new stuff. Okay, you already have your resource. Okay, just reuse your older resource as much as you can. Here, what do we treat our resource? After we calculate x squared, we treat x squared as our resource. How about that? X squared, we already have it. Okay, yeah. So later, when we have a chance, we use our older resource. Okay, we don't redo it. Okay, we do not recalculate x squared. All right. After we calculate x to the 4th, that's our resource. We use it, reuse it. Okay. After we calculate x to the 8th, reuse it. Okay? Reuse all the intermediate results you have already calculated and store in the temporary variables, yeah, because the storage very cheap. Store the data, the cost is very cheap, right? Yeah. So we're willing to pay some little cost. Yeah, we store our intermediate results, but that could be used to save a lot of time. Yeah. Here, when we calculate x to the 2 to the kth power, we use older resource, we can do much faster. Okay? So the idea, reuse your resource. Okay? Yeah. This idea. Yeah. Next, we do extension. Yeah. This time, we assume n is not power of 2. We want to use this same idea, reuse our resource to do the calculation, to save as much as we can. Okay? All right. A simple example. Before we do the generalization, let's run a relatively simple example to get some sense, to get some understanding. Yeah. Let's assume n equals 217. Yeah. What is the largest power of 2 under n? Yeah. So we want to use power of 2 to make this number, to construct this number, 217. Yeah. 128, 2 to the 7th, that's the largest power of 2 below this number, 217. Yeah. If 2 to the 8th, more than this number. So we should not use 2 to the 8th, okay? Yeah, big, yeah, more than this one. So we take this 128. Yeah. Yeah. So the fastest way to get x to the 128th, how many multiplications? The fastest way to get this number. 7. 7. 7, yeah, to get, yeah. But we need to reuse the resource, right? Yeah. When you get a 7, you already pay a lot of cost, right? You already pay a certain amount of cost. You pay, okay? Yeah. Yeah. Here we treat the time you used, computing time. Computing time, so that's the cost. You already pay for it, okay? Yeah. So we did intermediate calculation like this, x squared, x to the 4th, and so on through x to the 128th. Yeah. We treat this as these intermediate results, we treat as our resource. Okay? We should not waste our resource. We already have them. Okay? So next step, we should reuse this resource as much as we can. Okay? All right. Now, we decompose the number as the sum of powers of 2. Sum. Okay? All right. Yeah. Yeah. So we try to split. Yeah. 89, then we split 89 as 64 plus 25. 64 power of 2. 25 not, we split 25 as 16 plus 8 plus 1. Okay? Yeah. Yeah. Here, actually, you can see what do we get? Basically, the binary representation of 217, right? Binary representation. What we are doing here, basically the binary representation. Okay? Yeah. All right. Then, to calculate x to the 217th, yeah, because all the intermediate results we already have, we just do the multiplication in this way. Yeah, in this way. We need 4 more multiplications. How about that? After we get the first 7 multiplication to prepare, to do preparation, yeah, we treat as the first round, that part of the work, our preparation. After that, we just need 4 more multiplications to get it. So the final result, 7 plus 4, we need 11 multiplications. So to calculate x to the 217th, we need 11 multiplications. How about that? That's the technique, repeated squaring technique. That's the way we reuse our resource repeatedly, okay, as much as we can. That's the idea. Okay. Yeah. Try to get this idea. Okay. Try to generalize this idea. Reuse your resource. Okay. Yeah. Yeah. This general idea, later you can use it to solve many other questions. Yeah. Yeah. All right. General process. Now, after we studied this special example, now we feel we are ready to go to the general n number. Yeah. All right. General and find the largest k such that 2 to the k less than or equal to n. The first step. Because this number, you know what kind of preparation you need to do, right? Yeah. You prepare your intermediate results for next round computation. Yeah. All right. Yeah. You need k multiplications for your first round preparation. All right. Yeah. Since 2 to the k plus 1 strictly greater than n. Yeah, we know that. Yeah. Because based on the assumption, largest power of 2 less than or equal to n, if you add one more, that's strictly greater than n. Yeah. So we know this must be true. Okay? All right. Which implies that n is less than or equal to 2 to the k plus 1 minus 1. Yeah? Because we include the equal sign. Okay? So minus 1, so we can include that equal sign. Yeah? Because this is a strictly greater than sign. Okay? Yeah. So we can reduce it, that number by 1. Yeah. All right. Observe that 2 to the k plus 1 minus 1 equals sum of all these power of 2. Yeah. Do you know this formula? Can you see this simple formula? Yeah. The right-hand side is a special geometric series. Okay? The power of 2, can we treat as a geometric series? Yeah. With the common ratio 2. Okay? Yeah. The sum of it equals 2 to the k plus 1 minus 1. Yeah. From that, so that means we know this is the largest number that n can be. Yeah? Because n can only be smaller or less than this number. N cannot be larger than this number. Okay? That means if we use our already calculated power of 2, we can make n. Okay? We can just do sum of certain number of power of 2, we can get that n. Yeah. All right? Yeah. How to form x to the nth? How to form it? Yeah. Select elements from the set. Yeah. These terms, these numbers, they form our resource. We did the preparation, we get these numbers in the first round preparation, we get these numbers. Then, to get n, we only need to select some of the terms in the set and multiply them to get n. Okay? Yeah? Yeah. We only need to select some of them in the set. Okay? Yeah. Do you know how many elements in this set? How many elements in this set? K plus 1. K plus 1. Can you see that? K plus 1, not K. Can you see that? K plus 1. Why? Because x, the first one, corresponds to x to the 2 to the 0 power. Okay? 2 to the 0. 2 to the, this is 2 to the first. 2 to the 0, 2 to the 0, we take the exponent 0. 2 to the first, 1. Then 2 squared, 2. And through k. Counting by reference, how many numbers in this set? From 0 through k, how many numbers in this set? From 0 through k. K plus 1, right? Yeah. Here we apply counting by reference technique again. You need to, in order to, you need to establish one-to-one correspondence. Each term, you correspond to one component number. Okay, in this way. Yeah. All right. So there are k plus 1 terms. So you select some of the terms in this set. At most, k plus 1. That means if you do multiplication, at most you need k more multiplications, right? It cannot be more than k multiplications. At most, k more multiplications. Yeah. So the second round, at most, k more multiplications. The first round, k. Second round, at the most, k. Yeah. Usually smaller than k. Yeah. But the maximum number of multiplication is k. Okay? Yeah. So this gives you, if you use power of 2, if you use repeated squaring technique to calculate the monomial, here we are working on monomial. Yeah. What is the maximum number of multiplications? What is the maximum number of multiplications to calculate this monomial? This monomial. You can use this k number. What is the maximum number of multiplications? After our analysis. First round k, right? First round k. How many second round? Second round at the most k, right? Largest number is 2k, right? K plus k. First round k, second round at the most k. Could be smaller than k. So k plus k, 2k, the maximum. Okay? Yeah. All right? Yeah. 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 All right. This is the first. First, okay? Yeah. Yeah, at the most k more, okay? At the most k more for that. Yeah. So I'll ask you the maximum. Okay? All right. Next one, similar technique. Yeah. The idea exactly the same, but we just work on cube. Yeah. The previous one, squaring. How about we change squaring to cubing, right? And we can do the similar things. Yeah. All right. Repeated cubing technique. Yeah. Yeah. So let's, go through the same path. Yeah. Now we need to do some slight modification. Same path. Okay. All right. Why the structure of power of 2 is so special? Other than power 2, do we have other ways, right? Yeah, here. Can we work on structure of power of 3? Right? Yeah. Yeah. Let's consider the same example, n equals 227. But this time, we use power of 3 as our base structure. We replace power of 2 by power of 3 as our base structure. Yeah. This time. What is the largest power of 3 under n? Yeah, so this time is different. 81. 3 to the 4th, that's the largest. Because if we calculate 3 to the 5th, that would be greater than 217. Yeah, so we have to take this 3 to the 4th. All right. The fastest way to get x to the 81st power, 81st, 8 multiplications. Can you see that? 8 multiplications. Can you see that? All right. Let me show you, okay, how to get the 8. Yeah. First, in order to get x cubed, we need to use 2 multiplications. X times x times x. That's 2 multiplications, not 1. Okay, yeah. We do more. Yeah. Get x cubed. Next, x cubed times x cubed times x cubed to get x to the 9th. X to the 9th. 2 more multiplications. Okay? Yeah. 2 more. Next one, x to the 9th times x to the 9th times x to the 9th. X to the 27th. Another 2 more. The last one, x 27th times x 27th times x 27th, x to the 81st. See, each time 2 multiplications, and we did it 4 times. 2 times 4 equals 8. 2 times 4 equals 8. Okay? That's the best we can do. All right? Yeah. All right. Reuse the resource. Now, when we work on x to the 217th, we want to reuse our resource. Yeah. So let's look at our resource. Yeah. All these terms. So we already have these values. Yeah. So we should reuse them as much as we can to get 227th. 17th. Yeah. All right. Yeah. So this preparation step, we need 8 multiplications. Next round, yeah. The first round, preparation, 8 multiplications. Second round, to make that 217, we do decomposition as sum of powers of 3 this time. Okay? We use 3 as our base, not 2. Yeah. The previous one, the binary representation, right? Here we use base 3, we call it ternary representation this time. We do ternary representation instead of binary representation. Okay? All right. 217 equals 2 times 81. Why 2? Because in our ternary representation, we can use coefficient 2. 2 is less than 3, right? If the coefficient number less than 3, we can use it. Okay. Binary, because the coefficient number must be less than 2. Only 1 and 0, right? You cannot use 2. Okay? Only 1 and 0. Here, ternary representation, we can use our coefficient number less than 3, so 0, 1, and 2. We can use 2. Yeah. All right? Yeah. 2 times 81 plus 55. Next, we need to represent 55 as ternary representation. Okay? 55. Yeah. 2 times 27 plus 1. Okay? 2 times 27 plus 1. Yeah. Here. Yeah. Coefficient 2 is allowed to use. Okay? Yeah. To add power of 3 numbers. Yeah. All right. After this decomposition, let's do the final multiplication to get our destination. All right? Yeah. 2 to the 217 equals, corresponding to these numbers, we should use 2x to the 81st to do multiplication. We take 2, okay? When you see 2 here, we should use 2x to the 27th terms, do multiplication here, okay? 1, you just use 1x, okay? Yeah. So you get 5 terms to do multiplication. These 5, you need 4 more multiplication, right? Yeah. 4 more, yeah. Finally, our answer, 8 plus 4 equals 12. So use repeated cubing here. Our final answer, we need 12 multiplications. One more than our previous repeated squaring, right? Repeated cubing, we use 11, remember? 7 plus 4. Here, 8 plus 4. Here you can see one more than our old method. But that is for 217, right? Yeah. If for other numbers, probably this one can do better than the previous method, right? Yeah, it's possible. Yeah. This one can do better. For example, 15. Yeah. Let's do x to the 15. if we use repeated squaring, how many multiplications we need? X to the 15. How many do you need? Anyone has quick answer? Good, 6. 3 plus 3. 3 plus 3. 3, why 3? The first round preparation, we have 3. Yeah. X squared, x to the 4th, x to the 8th, 3. Second round, you need 4 terms multiplied together. X times x squared times x to the 4th times x to the 8th. 4 terms multiplied together, you need 3 more. 3 plus 3, use repeated squaring. Yeah. Here, our first method, we use repeated squaring. We need 6 multiplications. Okay? All right. Now let's try repeated cubing. How many multiplications we need? Repeated cubing. All right. Let's try a little bit. Yeah. 15 equals 9 plus 6, right? Yeah. Because 6 equals 9 plus 2 times 3, right? Yeah. When you do preparation to get x cubed, x to the 9th, how many multiplication you need? When you do your preparation, 4, right? 4, right? Yeah. Then, the second round, based on this, when you form x to the 15th, x to the 9th times x, how many more do you need? 2 more, right? 2 more. 4 plus 2, also 6. Also 6. Also 6. Okay? Yeah. Yeah. If you try 27, then this cubing one doing better, right? Yeah. Because 27 power of 3. Power of 3. So you take advantage of the cubing structure more. Repeated squaring, to get 27, you need to do more work. Yeah, you can try, yeah, but definitely the cubing one is faster. Yeah. Here you can see our conclusion. Sometimes repeated squaring one is faster. Sometimes repeated cubing one is faster. Right? Yeah. Depends on the number n, the structure of the n. Yeah. Okay? All right. Yeah. All right. Which method, the repeat squaring or repeated cubing, performs better in general? Yeah. Yeah. You cannot say one is clearly better. Sometimes this one better, sometimes that one is better. All right? Yeah. Okay. So then, in our project 1, I will do Horner's rule, brute force method, then I add a repeat squaring, then add a repeated cubing. Okay? Yeah. So then you know, do things together. So for our first project. Okay? Yeah. Any question? All right. Yeah, next. C.5. Take advantage of the structure of Pascal's triangle. Yeah. Have you heard of Pascal's triangle? Yeah. Some interesting structure in math. Yeah. Yeah. So let me explain this Pascal's triangle. Yeah. All right. Here, this topic, we want to consider a special polynomial, non-monomial. Yeah. The previous 2 topics, we only consider monomial, right? Yeah. This time, We look at non-monomial polynomial, but it has a very special structure. We can take advantage of that structure to use much fewer number of multiplications. Here, this topic. Yeah. All right, so let me show you. What's that? First, I want to introduce, give you this concept. Yeah. Pascal's triangle concept. Yeah. All right. Yeah. Look at this triangle, okay? These numbers, these numbers, we get them by a special way of multiplications. Yeah. So you will see these numbers are very special. So let me explain how to get these numbers. Yeah. All right. We use binomial formula. So these numbers, each row, if you look at each row, they correspond to one specific binomial expression. Binomial expression. Monomial, binomial this time. All right? Yeah. So what's the binomial? Two terms, by two terms. Monomial, one term, right? X to the nth. Two terms, x plus y to the nth power. That's the binomial. So there is a binomial formula. Okay. Now, when you learn your discrete math, if you still have the discrete math book, you can look at, pretty at the end, near the end, you can see this binomial formula. Yeah. People also call it Newton's formula. Yeah. Newton discovered this formula, Newton's formula, binomial formula, all right? Yeah. We need to use combinatorial numbers. Yeah. Here, parenthesis, this combinatorial numbers, okay? All right. So if we do the binomial expansion, we can use these combinatorial numbers, then to write individual terms in this format. That's the binomial formula. A question, how to calculate these combinatorial numbers? There is a formula using factorial to do the calculation, the formula, okay? Yeah. All right, so the formula to calculate, we choose, it's called choose n over k. Yeah. Yeah. Choose nk. Okay? Yeah. All right. Definition. This combinatorial number is defined as this fraction expression n factorial over denominator k factorial times n minus k factorial. Okay, yeah, that's the definition of this combinatorial numbers. Yeah. Then, with this definition, so you will see the top, the first row corresponds to the binomial expression with n equals 0. 0, yeah, so that's anything to the 0, that's 1. Okay, all right. The second row corresponds to the coefficients of x plus y to the first. N equals 1. 1 coefficient. The third row corresponds to x plus y squared. If you expand the coefficients, 1, 2, 1. Okay? All right. Then x plus y cube, 1, 3, 3, 1. All right? Yeah. Next one, x plus 1 to the fourth, 1, 4, 6, 4, 1. Okay? Yeah. To the fifth, yeah. Next row, to the sixth, to the seventh. Yeah. So you get this special triangle. So it's called a Pascal's triangle. Okay. The Pascal's triangle has a nice property. Yeah. So what's the property? Let's say any number equals 2 on its shoulder. Okay? Yeah. Yeah. Two numbers, sum of the two numbers on its shoulder. Okay? Yeah. The previous row, left side, left one, and the right one. Okay? Yeah. to the sum. It's true everywhere. Okay? Everywhere you have this property. Okay? Yeah. All right. Yeah. So now, after you understand this Pascal's triangle property, now let's use this understanding to solve one special question. Yeah. The question is, we want to calculate the polynomial with this given coefficients. 1, 5, 10, 10, 5, 1 special coefficients. Okay? Now you know it corresponds to one row in the Pascal's triangle. Right? Yeah? Yeah. After you identify the coefficients corresponds to one row of Pascal's triangle, you can write it as binomial expression, right? Yeah. If you apply, if people cannot identify it corresponds to one row of Pascal's triangle, people just use Horner's rule, right? Yeah. If you use Horner's rule, how many multiplications you need? How many multiplications? Horner's rule. 4. 4. Not 5. Not 5, because the leading coefficient is 1. Leading coefficient is 1, so you can do 1 fewer. Okay? Yeah. 1 fewer. Yeah. Not 5, it's 4. Yeah. Horner's rule. Yeah. Pretty good, not bad. Yeah. But if you can identify as Pascal's triangle, yeah, then you write as binomial expression first. X plus 1 parenthesis to the 5th. Addition, we don't worry about addition, right? We do one addition. So we calculate x plus 1 first. Then this number, we multiply itself, we get x to the 5th. How many multiplications do we need to calculate x to the 5th? First one, x plus 1 times x plus 1. The first one, x plus 1 squared, 1 multiplication. Second, x squared times x plus 1 squared times itself, second multiplication. Then one more, yeah, x plus 1 to the 4th times x plus 1, third multiplication. So we need a total 3 multiplications. We can save 1, right? Yeah. Yeah. Here you can see, if we take advantage of the special structure, Pascal's triangle, yeah, if you can identify it, all right, yeah, so then you can save certain number of multiplications. Okay, yeah, so that's another special case, some interesting special case to let you know. Okay, yeah, all right. So that's how much I plan to do regarding polynomial evaluations. Yeah. All right. Okay. Yeah. So then we move to next topic. Yeah. Yeah. Already. Yeah. Not much left. So here we just finished part C. Yeah. Next we start part D, our last part of this module. Part D, yeah. All right. The topic, optimality of algorithms. Another interesting topic in algorithms, that's the optimality issue we want to discuss in this part. Yeah. D.1, let us solve one easy, this problem pretty easy, but very useful. Yeah. Very simple, but very useful. It's the minimum selection problem. Yeah. First, it's a selection problem. First, I talk about selection problem. Then, this is a special selection problem, finding the minimum of an array. Yeah. All right. Our problem number 3, find the minimum of an array. Yeah. Given an array, definitely unordered, our goal, we need to find index I such that A of I is the minimum of the array. That's simple, right? Yeah. Everyone here you can find quickly, I believe, right? Yeah. Straightforward, so simple. Yeah. But we have a lot of things to learn in this simple computing problem. We have a lot of interesting things we can learn. Yeah. First, the problem type. We call this is our first selection problem. Yeah. The problem type is one of the 3 basic question types in this class, selection type. Yeah. So far, we learned search type before, right? Yeah. Search type, linear search. Okay? Yeah, search type. Here, the selection type. Yeah. Next class, we will learn sort, third basic type, sort. Yeah. Yeah. The reference here, I give you, these 2 sections, 2.3 and 4.5, 2 sections related to this topic. Yeah. All right. First, let me give you the definition of the selection problem. Yeah. Find the kth smallest element in a given array. Yeah. First, you're given an array. Yeah. Also, you are given this k number, integer k. Then you need to find the kth smallest element. This question is called a selection problem. Yeah. When k equals 1, first smallest, right? That's the minimum. When k equals n, the nth smallest. That's the maximum. So you can see the selection problem contains finding the minimum problem and finding the maximum problem. Yeah. All right, the special case. K equals 1 and k equals n. Yeah. And there is another one. K equals the index in the middle. That one, finding the median. It's also another important selection problem. Finding the median. Yeah. So later we will have a lot of discussion about finding the median problem. Another selection problem. Yeah. All right. Let's do some analysis. Initialization. Yeah. When we start, first let's look at the solution. So simple, so we can quickly go through it. At the beginning, let's use a special variable. Here we call it min. This min variable, min, to store the first element of the array as the initialization step. Then, as a general step, we compare the min value with the current array value, because we scan this whole array from left to right by incremental the index I number. Each iteration, we compare min value with A of I value. Two cases. If min value is greater than A of I, we update this min variable with a smaller element value, A of I. Okay? Otherwise, less than or equal, we do not update it. We just move to the next iteration. Okay? Yeah. So next iteration, we compare min and a of I plus 1, and so on. Okay? Yeah, the same thing until I equals the index of the last element, n minus 1. Yeah. After that, after we finish all the iterations, then we can return the value stored in this main variable. We get the answer. Yeah. That's the answer. All right? Yeah? All right. That's the solution details. That's the implementation. Yeah. Yeah. Everyone knows how to solve in this way. Yeah. So our main point, main discussion is not here. Okay? Yeah. Our main discussion, we want to see if this algorithm can be further improved. Can we do better than this? Yeah. First, let's see how many comparisons do we need in this algorithm. Yeah. How many comparisons do we need here? Correct. N minus 1, not n. Okay? Not n. N minus 1. Yeah. Can you tell me, can you explain to other students why you use n minus 1, you do not use n? Yes. At index 0, we do not do comparison. At index 0, this is assignment. Assignment operation we do not treat as comparison. Okay? Yeah. So for the first element, only assignment. We only do assignment, no comparison. After the first element, then each one we do one comparison. So we only do n minus 1 comparisons, except the first one. No first one comparison. Good. Yeah, that's the answer. But the next question is this n minus 1 number is the best we can do? Can we further improve it? Can anyone improve it, reduce this number to n minus 2? Only one better. We do not need more. We only want to do one fewer comparison. Is it possible? That's the question. Yeah. That's the main topic of this part. Yeah. All right. Yeah. So how do you see? Yeah. So we just discussed. Yeah, because we do not count that assignment operation. Okay, yeah, that's different. Yeah. All right, we only count comparison. Yeah, by reference. Yeah, because the first one, no one-to-one correspondence. Okay, after the first one, there is one-to-one correspondence. Yeah, so that's another application of this counting by reference method. Yeah. All right. Yeah. So yeah. One-to-one, yeah. All right. Next, is it possible to further improve the algorithm? Yeah. Yeah. We only have two options. In this situation, usually, people have two options. Yeah. The first option, try your best to improve the algorithm. Yeah. The first option. Yeah. But the problem is you may not be able to do that, right? Yeah. You have limit people, so because we have our limit. Okay, yeah. The second option, convince people that this is already optimal. No? If you can convince people this algorithm is already optimal. Optimal means no room for improvement, right? Yeah. There is no room for improvement. You just accept the solution forever. Yeah. No chance to do further improvement. Just take it. Okay? And take it forever. Yeah. Yeah. If it's optimal. Yeah. So that's the optimality issue we want to discuss here. Yeah. All right. Post-solution thinking. Let's do some post-solution thinking. Yeah. we should try to improve the solution as much as we can. Yeah. But the solution may have been optimal already. We want to know if it's already optimal. If it's optimal, we just move on. Okay? Don't waste our time. It's already optimal. Yeah. But the question is, how do you know it's optimal? Right? How do you know it is optimal? That's hard. Yeah. That's a hard question. How do you know it's optimal? Okay, yeah. So we need to study the optimality issue, the hard part. Yeah. So let's see what we need to do in order to convince people this particular solution is already optimal. We need to understand that question first. Yeah. So the hard part, we need to consider among all possible algorithms. How do you show optimality? So we need to consider all possible such algorithms, right? Yeah. How to show that this one is optimal among all of other possible algorithms solving the same problem. We need to address that. Okay? Is that hard? Yeah. Among all possible such algorithms, yeah, we need to see if this current one is optimal. Yeah. Including unknown algorithms. Because among all possible, there are many unknown algorithms, right? Because some algorithms, they haven't been discovered, unknown, right? Yeah. Our future generations, they may discover some new algorithms, right? So we do not know what kind of algorithms they can discover. We do not know, so we treat them as unknown algorithms, right? But here, when you want to address this optimality point, you need to cover those unknown algorithms, right? Otherwise, how can you make the claim that your algorithm is optimal, right? So you have to cover all those unknown algorithms. Is it possible? Here the question is it possible to cover unknown algorithms? Think about that. How hard it is to cover unknown algorithms. Okay? Yeah? Yeah. All right. Yeah. Is it possible to study unknown algorithms? Right? Unknown. How can you study unknown things? Think about that. Okay? Think about it. Here, we want to study some unknown objects. Unknown objects. Is it hard? Yeah. It is hard. The question, is it possible? By logic, think about, by logic, use your own logic. Is it possible to study unknown algorithms for general people? Not you. For the whole mankind. Yeah. Not just you. For everyone on earth. Okay, is it possible to study unknown algorithms? Okay, all right. Yeah. Let me finish the slide. Answer is yes. Answer is yes. Okay, it looks strange, right? How can you study unknown algorithms? Answer is yes, because let me give you the last critical sentence. So we finish this class. Yeah. How to study unknown algorithms. Discover some common property or properties for all those algorithms. If you can discover certain unknown property, yeah, although we do not know those algorithms, but we know they should satisfy certain unknown common property. Then we can study all those algorithms using the common property. The question is, if you can discover a common property. Okay? All right. So in next class, let's look at the common property shared by all those algorithms, including unknown algorithms. Okay? Yeah. All right. Yeah.